Good morning, everyone. Welcome back to VKP Online Tutorials. Today we will discuss numericals on traveling salesman problem or routine problem. Let's start with this numerical. Solve the following traveling salesman problem. Is given some from city and is given two cities. A, B, C, D are the from cities and two cities. A, B, C, D are the two cities. So in order to solve this problem, we need to determine what will be the optimum route and what will be the corresponding cost for the given cost matrix. So this is the given problem. Let's see what will be the solution for this problem. So here, to find the best route or optimum route, we need to apply Hungarian method. So we already discussed what is Hungarian method and how to apply Hungarian method for the cost matrix in previous sessions. So in Hungarian method, so we need to follow row reduction, then we need to follow column reduction, then we need to go for allocation. So apply these three methods to solve the problems in a traveling salesman problem. So now I apply a row reduction. Let us see in the first row. Let us see in the first row. I have a cost matrix like this. Select the minimum element in the first row. This is my first row. Select the minimum element in the first row and subtract with other elements. Say, forget about the diagonal elements. I don't want these diagonal elements. So minimum element in the first row is 25 and subtract by 25 with other elements. So this becomes 0, 75 and 25 is 50, 45 minus 25 is 20. And similarly, repeat the same procedure for the second row. Look at the second row. This is my second row. The minimum element is 25. So I'll subtract with other elements. 35 minus 25 is 10. And forget about the diagonal element. And 150 minus 25 is 125. 25 minus 25 is 0. Go to the third row. The third row, minimum element is 15. So I need to subtract with 15 from other elements. So 35 minus 15 is 20. Then 40 minus 15 is 25. I forgot about the diagonal elements. 15 minus 15 is 0. Then go to the fourth row. In the fourth row, the minimum element is 65. So 65 minus 65 is 0. 75 minus 65 is 10. Next 130 minus 65 is 55. It is 55. And forget about this diagonal element. Forget about the diagonal element. So this is about row reduction. Next, we need to apply. We need to go for column reduction. We need to go for column reduction. So in the column reduction, see this is the first column. Identify the minimum element and subtract with other elements. So in this column, identify the minimum element and subtract with other elements. In this column, identify the minimum element and subtract with other elements. Similarly for the last column. So now I'll take this table. Now in the first column, the minimum element is 0. Forget about the diagonal elements. I don't want these diagonal elements. The first column minimum element is 0. 10 minus 0 is 10. This is 20. This is 0. In the second column, minimum element is 0. So this is 0. This is 25 minus 0. This is 10 minus 0. In the third column, the minimum element is 50. So this become 0. Then this is 125 minus 50 is 75. And this is diagonal element. And 65 minus 50 is 15. Next, in the fourth column, minimum element is 0. So I'll subtract with other elements. 20 minus 0 is 20. The 0 minus 0, the 0 minus 0, and forget about the diagonal elements. Now go for allocation. Third step is allocation. In allocation, identify a row or column having single 0 and allocate that 0 and cancel the corresponding column and row vice versa. Now see the first row having two zeros. I'll not allocate the first row. And go to the second row. In the second row, we have single 0. I'll allocate this 0 and I'll cancel the corresponding column. This is my corresponding column. I'll cancel the corresponding column. And go to the third row. Third row, we don't have single 0. We don't have 0. In the fourth row, we have 1 0, single 0. I'll allocate this row and I'll cancel the corresponding column. This is my corresponding column. Next, go with column wise. Say this is my first column. This is my first column. I have single 0. Allocate this 0 and I'll cancel the corresponding row. So my corresponding row is this is my corresponding row for this column. Now go to the third column. We don't have 0. So in this case, number of allocations are 3, but size of the matrix is 4. Therefore, the solution is not optimum. Solution is not optimum. Solution is not optimum because number of allocations is not equal to size of the matrix. To get the optimum solution, so I will do reallocation. Just I will do reallocation. So I'll take the this so now see in uncancelled cells, say 25 is not cancelled, 10 is not cancelled, 75 and 15 is not cancelled. So pick least element. So my least element is 10. So from 10, I'll subtract other elements with 10. Only for uncancelled elements. Say forget about the diagonal elements. I'll not disturb the diagonal elements. Okay. So now this become 25 minus 10 is 15. This is 10 minus 10 is 0. And this becomes 75 minus 10 is 65. This is diagonal element. 15 minus 10 is 5. I cancelled. Next, identify the elements having intersection. Say 20 having intersection horizontal as well as vertically. So I'll add this 10 to this 20. So this becomes 30. And even this element is having intersection both horizontally as well as vertical, but it is belongs to diagonal. I'll neglect this element and write down the remaining element as it is. Here is a 10, this is 20, this is 0, this is 0, this is 0, this is 0, this is 0. So now I'll go for allocation. I'll go for allocation, row wise as well as column wise. Look at the first row. First row having two zeros, I will not allocate. Go to the second row. In the second row, you have a single zero. I allocate this zero and I will cancel the corresponding column. This is my corresponding column. I am cancelling. Similarly, go to the third row. In third row, we don't have zero. In the fourth row, we have two zeros. I will not allocate. Next, go with column wise. Look at the first column having single zero. I allocate this zero and I will cancel the corresponding row. This is my corresponding row. Go to the next column, second column. Second column having single zero. I'll allocate this zero and I'll cancel the corresponding row. This is my corresponding row. Next, go to the next one. We don't have zeros. We don't have zero in the third column. Again here, number of allocations are 3, but size of the matrix is 4. Therefore, the solution is not optimum. Again, we are not getting optimum solution. Next, to get the optimum solution, again repeat, again do reallocation. And reallocate to get the optimum solution. Now, diagonal elements, I'll mark infinity for diagonal elements. Diagonal elements, I will not give preference for the diagonal elements. This is diagonal elements. Now in uncancelled cells, say you have 10, 20, 15 and 65 are the uncancelled elements. So pick the least element. So my least element here is 10. So we need to subtract other uncancelled elements by 10. So this become 10 minus 10 is 0, 20 minus 10 is 10, 15 minus 10 is 5, and 65 minus 10 is 55. And identify the two intersection lines. Say 30 having two intersection lines, horizontal as well as vertically. I will add this 10 to 30, and this become 40. This become 40. And here also you have some intersection line, but this is belongs to diagonal. I will not disturb this element. Now write down the remaining elements as it is. So this is 0, this is 0, this is 0, this is 0, this is 5, 0, and this is 0. Next, go for a reallocation. Go for reallocation. Identify, look at the first row having two zeros. I will not disturb, I will not do any allocation. Second row having two zeros, I will not allocate. Look at the third row. Third row having single zero, I allocate this one and I will cancel the corresponding column. This is my column, corresponding column. Next, go to the third row, fourth row. We have two zeros. I will not allocate. Go to the column wise. Go to the column wise. This column having two zeros. This is 2 0. This is single zero. This column having single zero. Therefore, I allocate this element and I will cancel the corresponding row. This is my corresponding row. I will cancel the corresponding row. Next, again repeat the same procedure for column wise as well as row wise. Say this row having single zero, I allocate this zero and I cancel the corresponding column. Say my corresponding column is this one. Next, look at this one having single zero, this having single zero. I allocate this zero and I'll cancel the corresponding column. So my corresponding column is, this is my corresponding column. So now look at the number of allocations. Number of allocations equal to size of the matrix. size of the matrix. Therefore, the solution is optimum in case of assignment problem. Solution is optimum in case of assignment problem. Now, we need to cross check whether this will be applicable or suitable for traveling salesman problem, whether it is matches with the conditions of traveling salesman problem. Say this is the starting routes from route, and this will be the two routes. This is the A, B, and C. This is D. Now, look at the allocations. Look at the route. A traveling salesman, he will reach from A to C. He will reach from A to C. Here A to C. Then from C to D. You will go to D. Then from D to B, you will go to B. Then from B to A. So this holds good conditions of traveling salesman problem. Now we need to determine optimum cost for this route A to C. Just I will check the values. A to C is 75 rupees. A to C is 75 rupees. And C to D. C to D is 15 rupees. And D to B. So D to B is 75 rupees. And B to A. So B to A is 35 rupees. Therefore, the total cost is 75 plus 15 plus 75 plus 35. So we are getting 200 rupees. So this is the total optimum cost for the traveling salesman problem. And optimum route is A to C, C to D, D to B, and B to A. So this is the optimum route, and this is the optimum cost. This is the optimum cost. So with this, I'll conclude my today's session. Thank you.